So we're going to start with derivatives with respect to velocity. And this is just a little bit tricky because we actually, we don't usually know things with respect to the velocity terms that we need them. So for example, we need some derivative of a function with respect to u, right? Well, we usually don't, in the aerodynamic world, we usually don't think of things in those terms. We usually have things defined, so some coefficient is a function of total velocity v, alpha, and beta, are aerodynamic angles, okay? That's how we usually think of these coefficients. They're functions of v, alpha, and beta. And now we need to take the derivative of those with respect to u, little v, little w. So to do that, we need to just remind ourselves a few definitions here. So capital V is equal to the square root of u squared plus v squared plus w squared. Alpha is universally defined to be the arctangent of w over u. And we're actually going to use the small angle approximation for this, which is just w over u. Okay, now beta has two different definitions. So there's an aerodynamic version, or this is sometimes called the flank angle. But anyway, this is defined as tangent minus 1 of little v over u. And the experimental version, or the traditional definition of beta, I should also say, is equal to a sine minus 1 of little v over capital V. All right. Now, it actually doesn't matter which definition of beta we use, because once we use the small angle approximation for this, both of these simplify to little v over little u. Okay, so just in general, we're going to be calling this beta, but we're going to be using the small angle approximation for that. Okay. Okay, so let's look at this first term here that we need. I'm just going to move this down here. So the partial of some function with respect to u. All right, and I don't know what that is exactly yet, but I know that I can rewrite that as the partial with respect to capital V times the partial of capital V with respect to u, plus the partial of that function with respect to alpha times the partial of alpha with respect to u, and plus the partial of that with respect to beta times the partial of beta with respect to u. Okay, so we don't know this derivative yet directly, but I know that I can rewrite it in terms of these if I know these derivatives, this dv du, d alpha du, d beta du. Okay, and so I can actually just I can say the same for derivatives with respect to v. So I'll just write these out here quickly. So we've got the partial with respect to capital V times the partial of v with respect to little v, plus the partial with respect to alpha, d alpha dv, and the partial with respect to beta times d beta dv. And then the same with partial with respect to w, and that's the partial of f with respect to capital V, dv dw, plus df d alpha dw, plus df d beta times d beta dw. Okay. All right, so now we need to figure out what these derivatives are. These dv du, d alpha du, d beta du, d alpha dv, d beta dv. All of these we need now. So we can get those actually from these relationships over here. So the first one here, the partial with respect to capital V with respect to u. If you just take the derivative of this equation with respect to u, what we get is u over the square root of u squared plus v squared plus w squared. And so we can do the same dv d little v. We get the same thing except for little v. Get the same thing in the denominator, and dv dw, get the same thing with w over the square root of the same thing again, okay? Now, if we evaluate that well, let's come back to that in just a second. So now let's look at the partial of alpha with respect to u. And so we can get that from this equation here. The derivative of alpha with respect to u is equal to minus w over u squared. That's from the small angle approximation. The derivative of let's see, d alpha dv, little v here, is equal to 0 because alpha doesn't depend on v, right? And then d alpha dw, take that with respect to w, and we just get 1 over u, all right? And then the last three that we need here, I'm just going to squeeze them in over here, d beta du, and that's equal to minus v over u squared. Let me just shift this all over real quick. Okay, and then we've got d, that's a partial there, d beta d little v, and that is equal to 1 over u, and then d beta dw is 0 because it's independent of w, okay? So now we need to evaluate, so we can plug each of these in directly, first of all, okay? So we can take each of these expressions and plug them in for these expressions over here. But before we do that, I'm just going to simplify this a little bit by evaluating each of these at the equilibrium state. And let me put this in another color so we know that that's at the equilibrium state. So remember at equilibrium, we have u, v, and w equal to v naught, 0, 0, okay? So those are our velocities at equilibrium. That's simply by definition. So if I plug these in now, what I get here is this first one, we're just going to get u over the square root of u squared because both v and w are 0. So we're going to get a 1. The v is 0 here, w is 0 there. This next one is equal to 0 because w is 0. This guy's already 0. And then we have 1 over u, which is equal to 1 over capital V naught, our equilibrium velocity. And then up here, this guy's going to be 0 because little v is 0. This is equal to 1 over V naught. And this guy is 0 as well, okay? Okay, so now we can plug these all in, and at our equilibrium state, these derivatives then can be approximated by, well, we can just walk through here. So d alpha du is 0, d beta du is 0, and so we're left with just the first term here, df dv times dv du. dv du is 1. So this all simplifies to the partial of that with respect to capital V, okay? The next one, we've got dv is equal to 0. And d alpha dv is 0. And d beta dv is 1 over V naught. So we're left with the partial of f with respect to beta times 1 over V naught, all right? And then the last one, dv dw, is 0. d alpha dw is equal to 1 over V naught. So we're going to have a partial of f with respect to alpha times 1 over V naught. And then d beta dw is 0, okay? So this is our solution here. So anytime we need to take a derivative with respect to u, we're actually going to take that derivative with respect to capital V and say that that's equal to this within small angle approximations, and within this transformation of variables here from into alpha and beta. Whenever we need the derivative with respect to little v, we're actually going to take the derivative with respect to beta, because that's what we usually know in aerodynamic terms. We can get things with respect to beta and then multiply that by 1 over v naught to estimate this derivative here. And then finally, when we need a derivative with respect to w, we're actually going to take the derivative with respect to alpha, because we know that in aerodynamic coordinates, or the information we usually have on the aircraft with respect to alpha. So we'll get that and then multiply that by 1 over v naught to estimate what this derivative here is. Okay, so now let's get into some example, or our first forces and moment derivatives with respect to u, v, and w.